So here we're going to talk about another aspect of thermodynamics, and that is what is known as the enthalpy of formation. Now we know that we have a set of thermodynamic conditions which we need to sort of define for our laboratory conditions. And what this means is when we're doing experiments, there are certain experiments where the amount of energetics, the delta H, is a function, it varies slightly with temperature and ambient pressure. And so what we do to sort of make it so we're all sort of the same sheet of music is when we publish these numbers, oftentimes we will indicate what is known as standard state, which basically is, when we say standard state, all we're basically saying is, okay, I'm going to define this is the temperature and this is the pressure. So 1 bar of pressure, which is 10 to the 5 pascals, it's just a unit of pressure. So whenever we talk about standard state, it's 25 degrees Celsius and 1 bar pressure. Now the reason why we need this is because, again, all chemical reactions have certain thermodynamics depending on the temperature. And these conditions are sort of like standard laboratory conditions. So, when we do our chemistry lab here in Michigan, temperature is pretty close to 25 degrees Celsius and the pressure is pretty close to 1 bar. So we don't normally have to correct for our conditions not being a standard state because it's pretty much close enough. So what this means is we have what's known as the standard state sort of symbol. So when I talk about the delta H of a reaction, I put this little naught behind it, delta H naught. That means delta H at 25 degrees Celsius and 1 bar pressure. So this little circle tells you both the temperature and the pressure for a reaction. So this is the standard enthalpy of reaction. So standard is what that little dot means. It's associated with that because that means standard state. And delta H is just an enthalpy of reaction. So for anything with that little naught behind it, again, it's that measured quantity as measured at 25 degrees Celsius and 1 bar pressure. So we had mentioned that all balanced chemical equations have a delta H associated with them. We can now come up with the point where we can come up with a number and you can come up with a balanced chemical equation sort of on the fly. And what that is the standard enthalpy of formation, which is given the symbol delta H sub F naught. So it's a delta H naught, so it's a standard enthalpy of reaction, a delta H of reaction, standard state, and the only thing that's new is that F. And what that is tied to is the formation of 1 mole of substances from the reference elements in their standard states. So what this means is, so if I'm saying I want to determine what the delta H, how much the delta H associated with making, say, water from the reference elements in their standard states. And what do I mean by the reference elements? Well, they're essentially the elements as you would find them in their standard state. So if I went to the standard state shop and asked for some oxygen, some pure oxygen, it would come as a diatomic gas because that's what oxygen exists as when it's by itself at 25 degrees Celsius and 1 bar pressure. It's a diatomic gas. Or if I ask for aluminum, that is a monatomic solid. I ask for lithium, that's also a monatomic solid. Aluminum liquid, while I can have aluminum liquid and I can have oxygen liquid, at standard state, aluminum comes as a solid. So these are sort of like defined as a delta H of 0. So if I tell you the delta H of formation for a particular substance, you should be able to write me the balanced chemical equation associated with that delta H just using this definition. I know it's kind of confusing. It'll make a lot more sense if we do an example. So here is my example of methanol. So methanol, the delta H of formation, the standard enthalpy of formation, is minus 238.7 kilojoules. And so all delta H's must have a balanced chemical equation associated with them because it's an extensive property, so it makes a difference as how much we have. So we're going to essentially build our balanced chemical equation based solely on this definition, the formation of 1 mole of the substance from the reference elements in their standard states. So I'm going to start with my product. I know my product, it's the formation of 1 mole of this from elements in their standard state. So the easiest way to think about this is break it apart in pieces. So methanol is made up of 3 different elements. It's made up of carbon, hydrogen, and oxygen. I'm just sort of like writing the elements. Carbon, hydrogen, and oxygen. And they have to be the reference elements in their standard state. So the reference element is, I say, okay, what is carbon at room temperature at 25 degrees Celsius and 1 bar pressure, it's a solid. What is hydrogen at 25 degrees Celsius and 1 bar pressure? It's a diatomic gas. What is oxygen at 25 degrees Celsius and 1 bar pressure? It's a diatomic gas. So there are my reference elements. They're standard state. Say that 10 times fast. Now we have to balance it. Now there's only one balanced chemical equation associated with this number, and the definition is very clear. It's the formation of 1 mole, so I have to put a 1 there. But balancing these is always really easy, because you have a 1 there, and these are always free elements on the left-hand side. So I'm going to balance it. There's a 1, there's a 2, and I have to make that a 1/2. I do not have a choice. Can I multiply all these stoichiometric coefficients by 2 and then multiply the delta H by 2? That's fine, but what you would have to do is drop this little f, because that f has 2 implications. One is everything on the left-hand side is a free element in its standard state, and the other thing is that there's a 1 in front of this. So you would still have a balanced chemical equation and a delta H, but it would cease to be a delta H of formation. That's the critical point. Here's another quick one. So I tell you the delta H of formation for sodium carbonate is minus 1130.9 kilojoules. So I need a balanced chemical equation associated with that delta H of formation. So again, I have my product, which is sodium carbonate. The 3 elements that make up sodium carbonate are sodium, carbon, and oxygen. I look at sodium, and sodium is at 25 degrees Celsius and 1 bar pressure. It's a solid. Carbon is a solid. Oxygen is a diatomic gas. And then I have to balance it. I have to put a 1 in front of that sodium carbonate, and the spacing's off a little bit. I apologize. So I put a 2 there, a 1 there, and a 3/2 there. And she is balanced. Now, one of the cool consequences of this, and this is going to be a little tough, is another way of calculating the delta H of a delta H of some reaction. And the formula is kind of complicated, so I'm going to kind of take my time to sort of step through it. So the delta H for any particular reaction is the sum, that's what the little sigma means, of all the products of M times the delta H of formation of each one of the products, minus the summation of all the enthalpies of formation of all of the reactants multiplied by their stoichiometric coefficients. So M and N are the coefficients in front of each reactant and product in the balanced chemical equation. So a way of thinking about this is, okay, if we look at the delta H of formation of all the products, remember what delta H of formation is. And notice I have a lowercase f here, and I had an uppercase f on the other page. It makes no difference. It's just delta H sub f. Doesn't matter if it's capital or lowercase. So delta H of formation is the energy associated with the formation of 1 mole of a substance from its elements in their standard state. So if I multiply that by m, which is the number in front, that would tell me, so if I had a 2 in my balanced chemical equation, I take that delta H of formation, multiply it by 2, because it's how much energy it takes to make 2 moles from elements in their standard state. And I add up all of the energies needed for the formation of all of my products. So if I have 3 moles of this and 2 moles of this and 1 mole of this, I add up all those delta H's of formation, and it's basically how much energy is associated with making all of my products from scratch, from elements in their standard state. That's what this whole first part is. Now, for my reaction, whatever it is, generally it's not making all of those products from the elements in their standard state. But this is how much it would be if I made elements from their standard state. And then what we do is we subtract off the associated value for the reactants. So I look on my reactant side, I take each of my components in my balanced chemical equation, I take the delta H of formation of each one of those components, multiply it by the number in front of it, so this again is just the coefficient in front of each molecule or species in my balanced chemical equation, multiply it by the delta H of formation. And so that's the amount of energy needed to form all of my reactants from their standard state. But we are subtracting it off, right? This is how much energy it would take to make the elements in their standard state, the products, if I started with the reference elements. This is how much energy I essentially get, because of that minus sign, I get by taking all of the reactants and breaking them apart into their standard state. into the reference elements. Because that little minus sign is, I'm essentially changing the sign of all these delta H's, and I'm basically driving them all backwards. So I can think about my reaction as how much energy it takes to take all the reactants, break them apart into their individual pieces. How much energy is associated with taking all the reactants and breaking them apart into the reference elements, into O2 gas and aluminum solid, blah, 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 just sort of as a hypothetical. Then, how much energy it takes to the delta H associated with taking all those individual pieces and parts and putting them together to make my products. The difference would be that, because of Hess's law, the difference between those would be the delta H of reaction. And there are a couple samples, I'm sure, in your textbook of this particular sort of procedure. Sort of like a hardcore way of doing it.